So this is the third part of the video, and in this part you can see the algorithm in coloring a graph. So this is called the sequential coloring method, and of course you can see more details from the natural notes, okay? But I will use this PowerPoint and the video to give you more details for the method. So let me go back, and now before the end for the second video, okay, I just shown you this method, but now I will give you more details for it. Okay, now we will develop a method called sequential coloring, okay, to color a given graph. Well, actually it's very easy. Okay, so now first you arrange the vertex in some order, any order, okay, any order you like, okay, and then you prepare some colors, okay. So as I mentioned before, you can simply use alphabets for the colors, okay, A B C D E F G so on for the colors. So just to make sure that you have enough alphabet for the color, okay. So we to be safe, okay, we just prepare some colors for the vertex, okay, and then now we first we start coloring the graph. So for the very first vertex, we can always color it in some color, okay, because it's a starting point, okay. Just why don't we call that color A, okay. So we just color the first vertex by A, okay. Then now what next? Okay, so let me just go back here. Now here is the game, okay. After so here this is what I did for in the natural notes. So I just randomly choose some ordering on the vertex. So V1, V7, V9, V4, V5, and so on. So actually no reason, okay, just some order, okay, just like what I mentioned at the beginning. So according to this order, okay, I have to first color V1, okay. So that's why I give a color on V1 and I call that color A, okay, capital letter A. Now after you do that, then what next? Well, it's a very good bookkeeping practice, okay. So now let me explain it, okay. So now this is the notation for the color. We use that script C for the color. So C V1 means the color of vertex 1, and now that is capital letter A, okay. Now after we did the color, okay, then we look back to the graph, okay, and see what are the neighboring, what are the labels? What are the labels neighboring vertex for vertex 1? So for V1, you see it is connected to V4, V3, V5, V7, and V6. Okay, so that means those 1, 2, 3, 4, 5, 6 many vertex, they cannot be in the color A anymore, because remember, they are all labeled to V1, and now we put the color A on V1. That's why those 6 different vertex, they can no longer in the color A. Now, how can we remind ourselves that it cannot be the color A again? Well, this is the way to remind ourselves. We put the letter A next to those 6 vertex. So V7, V9, V4, V5, V3, and V6. Now remember, the color next to that vertex is not the color, okay? It's not the color of that vertex. It's the other way around, okay? So it's the color that you cannot use to color that vertex, okay? So that's the way to remind ourselves. And it turns out that it's very, very useful, okay? Because if we don't remember those relationships, then you will get lost, okay? And not just get lost, you will be wrong, okay? So that's why you really have to have a good bookkeeping method to bookkeeping your workings. Okay, now you you did it, okay? You did the labeling, okay? So V1 is in color A, and then you put the constraints, okay, next to the vertex. Now what next? Now the next thing you will have to do is to color the next vertex. So you already color V1, so the next one you need to color is V7, okay? Now for V7, you check what is the color next to it, okay? I mean, inside the bracket. Now, we know that, okay, because it's already next to V1, okay, just connected to V1, so it cannot be colored in A. So that's why you have to use another color on V7. So that's why when you color that, you use B, okay? That's why you see C V7 equal to B, okay? This is what you got from that constraint, okay? Now after you did the coloring, again, you just like the way you did for V1, you look at the labeling vertex for V7. So for V7, there are okay 1, 2, 3, 4, 5, again 6 vertex connected to V7. Okay, so including V1. Okay, we have V6, V5, V9, V8, and V2. So that means those vertex, they can no longer be colored in B. Okay, because V7 is already in color B. So those those vertex can no longer be colored by B. Okay, now and moreover, once you color that vertex, you can remove it from the list. So just like before, because you color V1, so in the second step, you couldn't see any V1 anymore. And after you color V7, okay, step 3, you see you couldn't see V7 anymore. Okay, so you remove those vertex which has color already. Okay, now after that, you have what? You want to color the next one, which is V9, okay? And then you look at V9. Now, inside the bracket, those are the constrained colors, okay? So those colors you cannot use. And you can see you have two colors. You have A and B as the constraints. That means V9 cannot be colored in A and B. So that's why you must use a third color. So that's why you use color C to color V9, okay? Again, once you color that, you look at V9, okay? V9, you have vertex 3, vertex 4, vertex 5, vertex 7, vertex X, okay, which are next to the vertex 9. And those vertex can no longer be colored in color C, okay? So that's why you put C next to V5, next to V3, next to V8. And those already have colors. You don't have to put any constraint because it's not on the list anymore, okay? Now after you color those vertex, you keep, okay, just repeat the process, okay? Once you finish it, you will get the coloring in this column, okay? And that is called the sequential coloring method, because we just color it in the sequential order, okay? We just do the coloring one by one, okay? We are not coloring those vertex all at the same time. That's impossible. Okay, you must do the coloring one by one, following the steps. Okay, and that is a very good way to bookkeeping your answer. Okay, so I don't really have to go back to the PowerPoint because the notes already got those details. Okay, so you of course you are welcome to go back to see the PowerPoint. Okay, so it's the same explanation as I just like what I did. Okay, and then I also include the stages in the PowerPoint. Actually, it's the same as the stages given on the natural notes. They're the same, exactly the same. Okay, just keep it here, okay? And then you see, we finish the coloring with 5 different colors. Okay, it's way below the number of the vertex, because in this graph, remember the vertex, how many vertex in this graph? We have 9 many vertex. Remember, we have 9 many courses, so that's why we have 9 many vertex. And now we can simply use 5 different colors to color the graph. That means we just need 5 different time slots, okay, for the exam schedules. So we reduce the number a lot, okay? Remember, if we don't know anything about this sequential coloring, we might simply use 9 different colors to color the graph, because we have 9 many vertex. But now we know this sequential coloring method, then we can simply use 5 different colors. So we reduce the number by quite a lot, by 4, right? In fact, we can improve this method. Well, the improvement is called maximum color selection strategy. Okay, so it's pretty long, but the concept is quite easy. Okay, because now where can we how can we improve the method? Okay, just actually for those algorithm is quite similar. I mean, in the sense that when you do the ordering, okay, we always have the freedom, okay, and that's exactly the point that we can do the improvement. Okay, remember at the very beginning, okay, for the ordering, okay, so let me just go back one more slide. Okay, not even here. So this is the original ordering for the vertex. Well, I just told you that, okay, there is no restriction on the ordering. You can just do it in any order, remember, in any order. Now, that is the point that we can improve it, because you can, you can always choose some specific order to color the vertex. And if you choose it in a better way, then you can reduce the number. And in fact, this is exactly the concept of the maximum color selection strategy. So let me go back to the notes. The PowerPoint. And you can see that. Now, what is this method? Okay. Now, in this method, we select from the list of uncolored vertex with the maximum number of color constraints. So we are not randomly choose the vertex to color. Okay, we choose the one with the maximum number of color constraint. Okay, so what is the meaning for that? For example, now at the very beginning, of course, okay, at the very beginning there is no colors on the vertex, so that's why you can choose any vertex to color at the very first step. So just choose V1, we put color A on it, okay? But once you put color A on V1, we will get some constraints on other vertex. So for example, for V3, you look back to the graph, because V1 is connected to V3, V4, V5, V6, V9, V7. So those vertex are connected to V1, so that's why you got those color constraints. So those vertex can no longer in the same color as V1, so we got the constraint. And the next step is to choose the one with the maximum number of color constraint. Well, here we have, okay, so we have 1, 2, 3, 4, 5, 6. So we have 6 vertex. They all have one color constraint. So among that 6 vertex, you can simply choose any one. Okay, but you cannot choose V2. You cannot choose V8, because those 2 have no color constraint. So that's why it's not the maximum. So maximum is here. Here is 1. Okay, so that's why you simply choose V3. Okay, so V3 has more constraints, so we color that first. So we choose V3. Okay, of course, if you don't like V3, you can choose V4, V5, V6, V7, or V9. Okay, but we have 6 choices, so just pick the one you like. So I pick V3, so it should be in the color B. Okay. Now after that, you have more constraint on the vertex, So for example, see V4, V5, V9. These three vertex, they both have two color constraints. So again, you choose the vertex among these three vertex because they have two color constraint, which is the greatest compared with other vertex, because others either have one or none. So that's why you pick V4 and then you color that in color C. And then in this after that step, you have another constraint on the vertex. So that's why you see V5 you have ABC, V9 you have ABC as well. So this time you choose the vertex among V5 and V9 because they both have three color constraints. So for example, you choose V5. So V5, now you put the color D on it. Okay, and then and so on. So every time you just choose the one with the maximum color constraint, then you will get the colors. Okay. Now you may wonder, okay, why that will give you less color. So it seems that every time you have to pick a new colors, right? So after V1, you have to color V3 with B, and then you have the color V4 with C, and then you have the color V5 with D, and so on. So it seems that you are using more colors. No, actually, you use the color. I mean, you used up the color at the very beginning, I would say. Okay. So after some step, you will see, for example, after you color with V9 with E, then actually for the remaining vertex, you don't need that many colors anymore because you already color those with the, I mean, so it's like you first tackle those troublesome vertex. Okay, so you finish the colors on those vertex, and then for the remaining one, they are not that troublesome. Okay, so you can save the colors for the rest. Okay, that is the idea behind this coloring process. And then see, okay, so for example, after V9, V6, you don't need F, okay, because in that step, you see, V6, okay, it has the color constraint A and C. That means no constraint on B or even D, okay, or E. So you can use some old colors to color those vertex. Okay, so that's why the number after that remain unchanged. So okay, so still, okay, in this method, okay, in this example, you won't see the big difference. Okay, still you need 5 many colors. Okay, but in fact, in general, the maximum color selection strategy actually can help you to reduce the number of color used. The exact reason why it works is because, as I mentioned, you use up those colors at the very beginning. Okay, you first tackle those vertex with more color constraint. Okay, you might use quite a lot of colors at the beginning, but after certain steps, you don't need that many colors after that. Okay, I mean, you just color those vertex, and then for the remaining one, you can use some old colors to do the coloring. Okay, so that's why that method works. Okay, and that will give you the less color. It gives you less many colors as possible to do the coloring. Okay. Well, actually, there's another remark I want to make. Okay, I didn't put that on the slide, but I just thought about that. And here, this graph, okay, in fact, this graph is not planar. Okay, that's why you can try. Okay, in fact, you cannot use 4 colors to color this graph. Now, actually, there's another way to see why a graph is not planar. Okay, planar, remember? Here I gave you the definition. Okay, did I? Yeah, I gave you the definition, actually. A planar graph is a graph that can be drawn on a plane such that any pair of the edges meets only at the end vertex if they do meet at all. In other words, no crossing. Okay, no crossing rather than at the vertex. But here, this graph, actually, this graph is the complete graph with 5 vertex. This graph is well known to be non-planar. Okay, no matter how hard you draw, there should be some crossing between the edges. Okay, not at the vertex, but at some point. If you have the crossing, then the graph is not planar. And look back here. In fact, you have that complete graph, okay, with 5 vertex hidden in your graph. So if it is the case, then you can imagine no way this graph is planar, because even this part is non-planar. How can you make sure the other part is planar? Okay, so that's why in this problem, I would say 5 colors is like the minimum already, because you know it cannot be colored in 4 colors. Okay, because you have this complete graph there, so it's already the optimal number. Okay, of course, yeah, that's another good point. Okay, for coloring graph, for graph coloring problem, of course you can always look at the minimum number of colors you need. Okay, you need to use. Well, but that may be a very challenging problem sometimes, because of course if the graph is planar, you know 4 colors is already optimal. Okay, because you can easily find some graph which is planar and needs exactly 4 different colors. For example, this one, this is a planar graph with 4 vertex. In fact, this is the complete graph with 4 vertex. And this graph, you must use 4 different colors to color it. There is no way you can use less than 4 many colors. So 4 is already optimal. Okay. But if the graph is not planar, I'm not so sure you can really say anything about the minimum color. Okay, sometime, because once the graph is not planar, it can be very complicated, because it might contains the complete graph and so on. So one way to really see any minimum number is you look at whether you have some complete graph hidden in your graph, just like this case. Okay, if you have the complete graph with 5 vertex, you will see you must use at least 5 colors. Okay, so yeah, so that's almost the end for this video. Okay, so I hope you all understand the concept and the materials for this chapter 8. It's not very difficult, but I would say it's a very it's an interesting application about graph theory. Okay, and it not just coloring any graph or any map. In fact, the interesting part is you can apply that to some problem like this. So, for example, finding some schedules, finding exam time slots for the classes. So actually, it's a very interesting application. Okay, and it really helps you to solve the problem. Okay, as just like what I mentioned at the beginning, because this problem we all have it. Okay, especially if you're a teacher, then you must know how to find the time schedule for the exam. Okay, but how can you solve the problem without too much pain? Okay, then in fact you have to know this algorithm sequential coloring. Otherwise, it will be very painful for you to solve the problem. And once you know this sequential coloring, you might have to develop some program. You can ask the computers to execute the program and solve the problem for you. Okay, that's the whole point for those algorithms. Okay, as I mentioned before already, why we have to learn the algorithm again, because not our human. Okay, we want to teach the computer to solve the problem, but the only way to teach the computers is to teach them through the algorithms. Okay, because they can only do some routine stuff. Okay, provided that we are not talking about AI. Okay, but in the old days, okay, we use the computer to solve tedious tasks, and algorithms is one of the good way in teaching the computer to solve the problem. Okay, once you can do it step by step in a clear way, the computer can do that. Okay, and not just they can do that, can do it in a better way than you. I mean, in the sense that they can be run, I mean, they can run the program in a much faster way. In particular, you don't need to do those tedious tasks. Okay, so that's the purpose for learning those algorithms. Okay, so that's the end for this video. I hope you all understand the material, and just let me know if you have any question. Okay.